Warm greetings to everyone. Today I'm going to deliver a video lecture on thin spherical shell, which consists of the internal fluid pressure small p in Newton per square millimeter and of diameter 150 mm and the thickness is small t. So it had to design that the thickness of the thin spherical shell, and the allowable stress in the material should not exceed 50 Newton per square millimeter. So in the case of thin spherical shell, both circumferential stress as well as the longitudinal stress are equal because of a spherical shape. Wherever you cut the section, it is of a circular one. So the circumferential stress F1 and the longitudinal stress F2 are equal. So therefore F1 is equal to F2, that is equal to PD by 4T. It is nothing but half of the hoop stress of thin cylindrical shell. So if you compare the same material and the properties of fluid and the other details are same, the thin spherical shell is more economical than the thin cylindrical shell. So here there is no maximum shear stress at anywhere or any section of the thin spherical shell. But in the case of thin cylindrical shell, you have the maximum shear stress. So that can be determined from sigma 1 minus sigma 2 by 2, that is the average of the major and minor principal stress. So here tau max is 0 and the circumferential stress is equal to the longitudinal stress. F1 is equal to F2, so that is equal to PD by 40. So here thickness we have to design thickness of the thin spherical shell. So thickness should be greater than or equal to PD by 4F, where F is the allowable or the working stress in the case of thin spherical shell. So if you are substituting the corresponding value, the fluid pressure is 2 Newton per square millimeter into the diameter of thin spherical shell is 150 mm divided by 4 into 50, where F is the allowable stress in the given material of the thin spherical shell. If you are working out, you are getting T should be greater than or equal to 3 millimeter, but it should not be less than 3 mm. So I am taking a minimum thickness is 3 mm. So what about the shear stress? Tau max is equal to sigma 1 minus sigma 2 by 2. So here F1 is equal to F2. So the principal stress are same. So see F1 minus F2 by 2, that is equal to F1 minus F1 divided by 2. What will happen? 0 by 2, it is 0. So nowhere the thin spherical shell is subjected to the shear stress. That is the major advantage of the thin spherical shell compared to thin cylindrical shell. Then we can able to find the what will be the corresponding diameter if the thickness is given. So that is the another design of thin spherical shell. So like that you can find any typical problem based on the thin spherical shell. So if the allowable shear stress, the fluid pressure inside the shell, and the diameter of the shell is given, you can find the thickness and you can find the corresponding major and minor principal stress. So here sigma 1 is equal to F1 and sigma 2 is also equal to F1 because both are same. F1 minus F2 are equal. That is PD by 4T. So therefore sigma 1 is equal to sigma 2 is equal to the corresponding value, that is PD by 4T. If you substitute, you will get the corresponding both value of the major and minor principals are equal. This is about the design of thin spherical shell. So the problem workload will be shown as here. So the compared to thin cylindrical shell, thin spherical shell is more advantageous. It will take more pressure if all the given parameters are equal, and also there is no shear stress at any point of or the cross section in the case of thin spherical shell, and so it will take more pressure compared to the thin cylindrical shell. So that is the major advantage of the thin spherical shell compared to thin cylindrical shell. Thank you very much for patient listening. God bless. வாழ்க வையகம், வாழ்க வளமுடன்.